In this video we're going to solve the Cauchy problem for the heat equation on an infinitely long rod, and we're going to do that using Fourier transforms. So in particular we're going to look at this problem here, the homogeneous heat equation defined for x anywhere in the real numbers, so that's the infinitely long rod, for times greater than 0, and an initial condition that says that when time is equal to 0, then u is equal to some function that we're considering to be known, which is the function f of x, defined for x anywhere in the real numbers. And we're going to show that this problem has got a solution of the form of this expression given in yellow. Let's begin by reminding ourselves what tools we can use when we're using the Fourier transform. So first of all we should say what the definition of Fourier transform is that we're using. Well, we're going to define Fourier transforms in this case with respect to x. So in other words we're going to say that when we take the Fourier transform of a function u of x and t, then that will give us a function of xi and t that we'll call u bar. So the bars are going to denote Fourier transforms with respect to x. And that is equal to the integral from minus infinity to infinity of the function u of x and t multiplied by e to the I xi x and integrated with respect to x. So that's the definition of the Fourier transform. Now we've seen in lectures that there's a derivative theorem which says that if you take the Fourier transform of a derivative, in this case the derivative with respect to x, because we're taking the Fourier transforms with respect to x, then that is exactly the same as minus I xi times the Fourier transform of u, or in other words minus I xi times u bar. So that's the derivative theorem. We've also got the convolution theorem. Here's the definition of convolution in green. But the convolution theorem says that if you take the Fourier transform of a convolution, then it's exactly the same as the product of the two Fourier transforms. So the Fourier transform of f convolution g is equal to the Fourier transform of f times the Fourier transform of g. And then finally in our toolbox we've got the Fourier inversion theorem, and that tells us how to get the function u of x and t back if we've got the Fourier transform u bar of xi and t. And the Fourier inversion theorem says that the way that we do that is we take u bar of xi and t, we multiply by e to the minus I xi x, and then we integrate with respect to xi between minus infinity and infinity, and then multiply by 1 over 2 pi. Okay, so those are the tools that we're going to use. What about our general overall strategy for solving the heat equation? Well, first of all we're going to use the derivative theorem and apply the initial condition, and that's going to allow us to show that u bar, the Fourier transform of u, is given by this expression here, f bar times e to the minus c squared xi squared t. So in other words, we first of all find an expression for the Fourier transform of u. Then the second step really is all about inverting the Fourier transform. So we've got an expression for u bar. How do we get back to u? Well, if we look at the right hand side of this expression in yellow, then we can say that the Fourier transform f bar is just the Fourier transform of f. So we know what the inverse Fourier transform of f bar is. But what about this other function here? What about e to the minus c squared xi squared t? Well, we're going to call that g bar, just to give it a name, and then we're going to try and find its inverse Fourier transform. And that's going to be where the Fourier inversion theorem comes in. That's going to allow us to find the function g whose Fourier transform is g bar. And then finally we'll say that, well, we have that u bar is the product of Fourier transforms. Well, the product of Fourier transforms we can use the convolution theorem to write as the Fourier transform of a convolution, and therefore u will be a convolution of f and g, and that will finish the derivation. Okay, so that's an overview of the strategy we're going to use. Let's start looking at it in a little bit more detail. So, first of all we should define what notation we're using. So we should say when we start writing the solution, define u bar in this way here. So that's the Fourier transforms with respect to x. and then we're going to apply Fourier transforms to both sides of the heat equation. So when we look at the term uxx in the heat equation, we're going to use the derivative theorem straight away, because the Fourier transform of the second derivative of u with respect to x, well, we can write that as the Fourier transform of the derivative with respect to x of du by dx. And then remember that the derivative theorem says that if we have the Fourier transform of the derivative of something, then that is exactly the same as minus I xi times the Fourier transform of that thing, in this case du by dx. Then we can say du by dx is a derivative itself, and so we can use the derivative theorem again. That means that we bring out another factor of minus I xi, and then we'll have the Fourier transform of u, or in other words, u bar of xi and t. And then finally, notice that minus I xi all squared will give us I squared xi squared. I squared is minus 1, so this is just minus xi squared times u bar. Now let's have a look at the other term in the heat equation, so ut. So if we want to take Fourier transforms of that with respect to x, then the Fourier transform of du by dt is just going to be du bar by dt. We're not going to use the derivative theorem here because Fourier transforms have been taken with respect to x, not with respect to t, and so the derivative theorem isn't applicable if we're looking at derivatives with respect to t. So that's nice and simple. And finally, we should note that the Fourier transform of 0, which is on the right hand side of the heat equation, the Fourier transform of 0 is just 0. You can see that very straightforwardly from the definition of Fourier transform. And so, combining all of that, if we take Fourier transforms of the whole of the heat equation of ut minus c squared uxx equals 0, then it gives this equation at the bottom here. So the Fourier transform of ut, we said, was the derivative with respect to t of u bar. Remember, u bar is a function of xi and t. And then we've got minus c squared times the Fourier transform of uxx. So that's going to be minus c squared times minus xi squared, giving us plus c squared xi squared, times u bar of xi and t equals 0. So that is now something that looks a lot more like an ordinary differential equation, because we started off with derivatives with respect to t and x. Now we only have derivatives with respect to t, and that's where the derivative theorem is so useful, because it's just allowed us to essentially turn a PDE into an ODE, and that should be easier to solve. Having said that, let's see if we can actually solve it. So here is the ODE again. It's not quite an ODE because really u is a function of two variables, xi and t, but we only have differentiation with respect to one of them. So it's like an ODE, but wherever we would have a constant, an arbitrary constant in any method that we apply to this from ODEs, we should replace that with a arbitrary function of another variable. So that's going to be an arbitrary function of xi in this case, because the differentiation is with respect to t. So if we look at this, it's first order and it's linear. That suggests that an integrating factor method might be a good idea. So let's do that. Let's have a look at an integrating factor. We choose e to the integral of whatever's in front of the non-differentiated unknown quantity. So we'd have e to the integral of c squared xi squared with respect to t, or in other words, just e to the c squared xi squared t. So we multiply absolutely everything by that. That gives us this expression here. And then you notice that these two terms, in fact, give us a perfect derivative. So if you need convincing of that, then you could work in the other direction and you could say, what would I do if I was asked to differentiate with respect to t, the thing in the curly brackets here? Well, hopefully you'd use the product rule, so you'd have the exponential times du bar by dt, which is this term here, plus c squared xi squared e to the c squared psi squared t, which would be the derivative of this exponential with respect to t, multiplied by u bar. Okay, so this is a perfect derivative. If we integrate both sides of this, then integrating with respect to t of the left hand side leaves us just with the thing from the curly brackets. On the right hand side we'd have a constant normally if it was an ODE, but because it's a PDE, that is an arbitrary function, let's call it c1, of the other variable psi. Then if we rearrange this, we have that u bar of psi and t is equal to c1 of psi times e to the minus c squared psi squared t. So now we've got an expression for the Fourier transform of u, an expression for u bar, but we've still got this arbitrary function c1 of psi. So to find out what that is, we're going to have to apply the initial conditions. But first of all, we have to apply Fourier transforms to the initial conditions. So remember our initial conditions were that u of x and naught was equal to f of x. So if we take Fourier transforms with respect to x of both sides of that, then we'll get u bar psi of naught on the left hand side, and taking the Fourier transform of f of x gives us f bar psi. And so therefore we can see that if we put t equals 0 into our general expression up here, then if we put 0 here, what do we get? Well, we'll have e to the minus 0 gives us 1, so this factor is just 1. And so u bar psi and 0 is equal to c1 of psi, which our initial condition gives us is just f bar of psi. So c1 of psi is exactly f bar of psi. And therefore, putting that into the general expression we found in the last step, we have that u bar of psi and t is equal to f bar of psi times e to the minus c squared psi squared t. So that's the first step of our plan that we detailed on the strategy part of the video done. So now we progress to the second bit, which is to say, can we find the inverse Fourier transform of the function e to the minus c squared psi squared t. So in order to do that, we're going to use the Fourier inversion theorem to find the function that we'll call g, whose Fourier transform is this function that we've called g bar of psi and t. This is going to be a process that has quite a few steps, but each of the steps are fairly simple. So first of all, this first line is just a statement of the Fourier inversion theorem. So it just says that in order to invert the function e to the minus c squared psi squared t, which is what we call g bar, all we do is we take 1 over 2 pi times the integral of that multiplied by e to the minus I psi x with respect to psi. Then to get to this second line, all I've done is combine these two exponentials, and then in the exponent I've factorised by taking out a common factor of minus c squared t. Now that might seem a bit artificial because you introduce this fraction, but the reason we do that is so that the leading term in the square brackets is going to be just psi squared. So this first step is really just simplifying. The next step is going to be to complete the square in the exponent. So we're going to write this as psi plus ix over 2 c squared t, all squared. If you think about multiplying that out, we would get psi squared plus 2 lots of ix over 2 c squared t psi, which would give us exactly this term. So these two terms result, but then we'll have a third term which will be this fraction here squared. And this fraction here squared would be I squared, which is minus 1, times x squared over the bottom squared. So we'd have minus x squared over 4 c to the 4 t squared. And so consequently we have to add that term back on. So we add on x squared over 4 c to the 4 t squared. So this step here, to get from the second line to the third line, we're just completing the square. Now what about the next line? Well, we can see that this last term is going to give us an e to the minus c squared t x squared over 4c to the 4t squared. There isn't a psi anywhere there, which is what we're integrating with respect to, so we can take that exponential outside the integral, and that leaves us with 1 over 2 pi e to the minus x squared over 4c squared t times the integral of e to the minus c squared t multiplied by this bracket that we've got squared with respect to psi. The next step is going to involve a couple of substitutions. So the first substitution that we're going to do is to look at this bracket here and call that, let's say, y. So y is going to be psi plus ix over 2c squared t. Okay, that means that dy is exactly d psi. And so if we make that substitution, we're going to get this expression here. So the integral becomes the integral from minus infinity to infinity, e to the minus c squared t, and then we've had the bracket squared before, now we've got y squared. Then the next step is going to be to make the whole exponent equal to minus z squared. So to do that, we're going to make the substitution that z is equal to c squared, well, in fact, z squared will be equal to c squared t y squared. In other words, we're going to define z to be the square root of this. So z is going to be c times the square root of t times y. In other words, dz is going to be equal to c root t dy. Okay, so when we write dy, well, dy will be dz over c root t when we make the substitution, so we're going to have a factor of 1 over the c times the square root of t coming in. But then the integral finally is going to be a nice one, because we're going to have the integral from minus infinity to infinity of e to the minus z squared dz. And this is a well-known integral, and although we haven't proved it in the course, you'd always be given this result. Then this integral is equal to the square root of pi. And so this whole integral simplifies really nicely just to the square root of pi. Therefore, putting that into here and simplifying, we get that g of x and t, after all of those steps, is equal to 1 over 2c root pi t e to the minus x squared over 4c squared t. Finally, let's collect together the results that we've got so far and use them to finish the problem. We've said that the Fourier transform of u can be written as the product of Fourier transforms. It's the product of f bar and g bar. And we further know what the inverse Fourier transforms of both of those functions are, because we know that the inverse Fourier transform of f bar is just the function f of x, and we also know that g bar of psi and t is the Fourier transform of the function that we've just found, so 1 over 2c root pi t e to the minus x squared over 4c squared t. So because we know that the Fourier transform of u is the product of two Fourier transforms, we can use the convolution theorem to tell us that the product of the Fourier transforms is exactly the same as the Fourier transform of the convolution. Remember, this is the definition of the convolution in green here. And then finally, if we apply inverse Fourier transforms to both sides of this equation here, then the inverse Fourier transform of u bar will just be u. So that will be u of x and t. And then the inverse Fourier transform of the Fourier transform of the convolution, well, those will just cancel each other out, the inverse Fourier transform and the Fourier transform. So we'll just have the convolution of f and g. Okay, so u will be the convolution of f and g. Here's the definition of convolution. All we need to do is apply that to f and g, and finally we get the result that u of x and t is the integral of 1 over 2c root pi t times e to the minus x minus y squared, this is g of x minus y, over 4c squared t multiplied by f of y and integrated with respect to y. And that completes the solution to the heat equation Cauchy problem.